Today we will be talking about the latest algorithms in machine learning that machine learning has to offer for computer vision. And so let me just straight right off the bat go to the things we will be discussing or looking at. So I have kept the contents very uh, high level, so not too deep in maths and all those kind of things, to give you a general idea of what the world or what the research community in computer vision and machine learning has been looking into. So first, we will of course look into the motivations as to why are we doing this, what are the applications, where do we see ourselves. So over there, we will be discussing of what is computer vision, what is machine learning in computer vision, and I shall give you like a small example of how you can do a hands-on thing if you want to go ahead and do the machine learning processes yourself. Then we will be looking at some of the, I would say, fun state of the vision, state of the art computer vision and learning techniques, and see what the world has been up to in the last 5 years or so. And then, of course, I will throw you some pointers as to where you can go to look up these things, learn more about it. So you will just mainly get an overview from this. And then I will be talking about job opportunities as well. All right, so motivation. And so this will be your introduction to computer vision and machine learning. What is computer vision? So according to most people, computer vision are machines that are capable of seeing, right? So your system has an input which is like taking in pictures and it's processing those images and doing some meaningful output, right? So science fiction and thrillers have dealt with this for so many years. Hollywood, Bollywood, we have all been interested in these machines which are capable of seeing and they perform actions. So these are some of my favorite movies, and they deal with some of the philosophical aspects of machine learning and ethics as well. So if we have a robot powerful enough, then where do we go with that? How we interact with that system, and so on and so forth. So check out these movies for funsies if you have. Like Ex Machina and 2001: A Space Odyssey, these are very classics in the field. So what is a computer vision system, right? So when would I classify a system as computer vision system? So first of all, it needs to have a visual input system, which means your input to the system should be either an image, a video, or like an infrared image or ultraviolet image, which is like coming from specialized cameras, right? But there need to be a vision system. Once the machine has this image or the video, second step is to parse and understand the input. So which means they are taking the video and they're trying to analyze the content of the video, seeing what's inside the video. So for instance, in this case of GIF fragment, you see that the machine is able to identify what are the different people who are walking. It's able to identify cars and umbrellas and so on and so on and so forth. So this was actually a scene taken from Times Square in New York, and it's a vision system which performs real-time analysis of whatever is going on in the frame. So it needs to parse and understand the input. And the third and most important part is it needs to do some action. So not only understand the input, but then perform some actions. For instance, this application, what it does is when cars pass by the toll bridges, they automatically take a picture of the number plate and they parse the number plate and they sense, okay, this is the guy who is driving, and then send you the toll bill or send you a fine if you drove badly or something like that. And for instance, suppose this system, this image is taken from Wuhan's railway station. Yes, the same Wuhan of COVID. So they actually had a railway system where you don't need tickets if you need to enter the subway or the trains. So they will just take a picture of your face, analyze and see who you are, and send you the bill automatically to your account. They have linked it together. So you just walk right into a railway station and they'll take care of everything. So just imagine the complex computer vision system that they have set up, that they can identify every one of the passengers who's passing through the railways every day, right? And so once you have that, so computer vision system, of course, you require an understanding of shape, motion, color, texture, and all of these things in order to build and implement a system like, right? So now moving on. Now the point here is you need to understand the two differences. So without machine learning, computer vision has been around for like the past 10, 20 years, whereas computer vision is a relatively new technique, right? So I don't know if you guys remember, at least when I was little, in India, we used to have an advertisement of Canon cameras. So Canon came up with this camera which detects your smile, right? So if you smile, it takes a picture and detects it automatically. So back then there was no machine learning. So what Canon did was purely based on like non-machine learning classical computer vision techniques. So you can do things like face identification, eyes and smile and identification. You can see what the flow of a traffic is or which way a pedestrian or a person is moving from a cam. And then you can perform image stitchings as well. So a panoramic image. So many of these things you can do with the classical computer vision technique at your disposal. But the problem is, as the kind of challenges you're looking for gets more complicated, just computer vision without machine learning was not doing a great job. So because it's hard coded essentially, it's hand coded, hard coded code. It's not learning anything. So if you have to do stuff like say emotion detection, so where you're not just finding if there is a smile, but you're trying to find the subtle emotions of fear, sadness, happiness, and so on and so forth. Or suppose you want to work on some specialized field such as medical image and you have to identify which is the tumor in a human brain or things like that. Or more advanced tasks such as not only identifying a car but tracking it and then seeing who the owner is and so on and so forth. So these kind of complicated operations were getting very difficult to do with like classical computer vision techniques without machine learning. So hence machine learning found its way eventually into computer vision. And then I think 2014 was the first time AlexNet was used. So middle of 2015, 2014 was the time when machine learning saw a surge, and then we got so many wonderful applications of it. Now let me introduce machine learning because we have been talking about computer vision a bit. Hopefully you understand what vision systems do. It's pretty intuitive to be honest. So machine learning, what is machine learning? So for all of you here who is software engineers or done some kind of coding, you may know this. So software engineers is you have the human created rules and you have some data and you feed both of them to find answers. So that means you may tell the computer, okay, my rule is y equal to x times 2, right? And so if you give in the data x equals 1, your answer will be y is 2. Whereas if you give in the data x equal to 2, your answer will be y is equal to 4. This is standard stuff for software engineering. So you give it some rules, some if then else statements, and the machine flows through it with some data and then gives you the final output. Whereas for machine learning, the thing is a bit different. So what you do for machine learning is you give him the data and you give it, I already called him. Anyway, you give the system the data and you give the system the answer. So you say, my data is 1 and my answer should be 2. My data is 2, answer should be 4. So it's for the machine to figure out that the rule was y equal to x times 2. Right? So now you can imagine how you can use this in a vision system. So we may give the system tons of pictures of cats and other tons of pictures of dogs and tell the system, okay, I want you to classify between cats and dogs. And the system has to come up a way by which he can say that, okay, I think if the picture has these kind of patterns, then I think it's a cat, versus if the picture has these kind of patterns, then I think it's a dog, right? So that's the kind of classification that machine learning or neural networks do. Right. So this is a typical look of a neural network. So I'm using the word machine learning and neural network almost interchangeably, which is not true in certain settings. But since for today's talk, we will be like mainly talking with neural networks, so I've just done that. But there are so many other non-neural network-based machine learning as well. So now this is a neural network. So the thing that we are trying to do is, the left side, you see actual images of a brain that I've taken from some biology text. And over here, you see machine learning stuff. On the right side, we see a typical structure of a neural network, like artificial neural network, and this is the structure of a brain. So as you can see, artificial neural network has a bunch of nodes which is connected by edges or graph edges, if you may. And then each of these nodes is essentially a mathematical function. I'm not going into too much details as to how this mathematical function works, but if you remember how neurons work, so essentially there are input signals coming in, and if some of these input signals are strong enough, this nucleus or this thing is fired, and you get an impulse traveling through your axion. So this is middle school biology for us, right? So if these signals are stronger, then this neuron is fired, it's triggered, if you may say. So similar things happen in case of an artificial neural network. There are signals coming in. So signal may be, say, the pixel value of a picture. signal may be a word which is being taken from a sentence if you're trying to understand what the sentence is. So for natural language processing. So these kind of things are coming in. And then if your signal is strong enough, your neuron is getting fired and you get some output, right? So that's what, so these individual neurons are getting fired based on what your input is, and then you get some output. So that output can be classification of cat versus dog, or that output can be, okay, is this text in English or is this in Hindi or whatever. Based on your applications, you just arrange your neural network accordingly. Right. Let me give you an example of a typical computer vision neural network system. So suppose I have the image of this cat, right? And as you know, every image can be broken down into like red, green, and blue channels. So that's how images. So if it's a color image, there are three channels: red, green, and blue. So you can break them down into three channels. And then what you can do is you can take individually these channels, and then you can form a vector. So it means 255, 231, 42, 22, 123, 94, 83, 82. So you look at them row wise, sort of unwarp them, or like you vectorize them into a I'm doing so many hand movement, guys, trying to explain to you, and I remember my videos of. But anyway, so we take these row vectors and we arrange them in a long list of chains, right? So these are my red vectors, then is my green vectors, then is my blue vectors. So you have this long pixel chains, and that you feed into a neural network. So each of these neurons go over here. And then at the end, I make a rule that, okay, if my neural network outputs a zero, it's a cat. If my neural network outputs a one, it's a dog, right? So if it's a dog, it will output one. If it's a cat, it will output zero. So now what happens? I have, say, 500 images of a cat and 500 images of a dog in different postures, in different lighting, in different color, and so on and so forth. So the neural network will take in those pixel intensities, see what the output is. If the output is wrong, so it will go forward, see what the output is. If it's wrong, so it will go back and then try to change whatever were these nodes values and whatever were these edge values such that it now fits better the output, right? So there is a continuous chain of cyclic processes going around as you feed it more and more images, and that's actually the learning process. So which means it again, so images are coming in, it sees the output and then changes the network such that the output is according to what the image should be, right? Once you have trained the network with say 500 images of cats and 500 images of dogs, now you know that okay, I have the network is trained, all the edges and nodes have certain values. Now you can just pass in a single image of a cat or a dog and ask the network that, hey, I already showed you these 500 images of cats and dogs, and you know what a cat and a dog is. So here is a new picture of a cat or a dog you have never seen before. What do you think? Is it a cat or a dog? Right? So then you analyze the machine learning network based on what new images it sees, and it gives you an accuracy of say, okay, these are the 10 or 100 new images I'm seeing, and I can correctly classify like, okay, so and so many cats and dogs, and so its accuracy is 90% and so on. So that's like a typical structure, right? So even if you have to use a network, you first train your network based on some previously seen images, and then you put it to use in whatever it was supposed. So you can already, I think, see a disadvantage of machine learning, if I may, which is that it needs tons of data before it can be useful in any sense, right? So if you're trying to create a system which will work for autonomous vehicles, right? That means for automatic cars. So that means you have to train it with like thousands of hours of videos of traffic videos of cars going in and so on and so forth. If you don't have the data, you cannot train a machine learning or a neural network. So again, I'm not trying to go into too much technical, but this is the general flow of a learning network. So I wanted to talk a bit about convolutional neural network because our topic is mainly on computer vision and machine learning, and convolution is a very powerful tool in convolutions and image processing, if you may say. So the problem with this technique was that whenever I am taking these pixel things and just putting them in a state or like unrasterizing them in a state vector, the problem is I lose all the neighborhood features. So that means in images, the neighborhood features are so important. So if this pixel, I can look at its neighborhood and find out that, okay, this belongs to an eye or this pixel belongs to a nose. But if I do this process where I just flatten everything, I'm losing that connectivity, right? So in order to counter for that, what people came up was the convolution. So if you look at this image, so convolution is each node, instead of taking a single pixel, is taking like an area as its input. So you can think of this as a lens. So it's looking at the picture through lenses of different dimensions, right? And that gives the network a chance to learn the different texture and like neighborhood features. So this is an eye, this is a nose, and so on and so forth. So this is a typical example of convolution. So you have an input image, you have say a matrix, which is the convolution matrix. And so if you multiply these two, you get the results of convolution, which is, so you get this kind of an image where you see all the vertical edges are prominent, right? So based on this image, the system can learn what the vertical edges are. Similarly, you can learn what the horizontal edges are, what the gradients are, and so on. So this is a typical example of a convolutional neural network. So I love this. So what they've done is they are giving you the, after this system is trained. So this system was supposed to output whether an image is a boat or a bird or a cat or a dog, and so on and so forth. So as you can see, it has taken this boat image as an input, and it's saying that I think with 94% probability, this guy is a boat, and 0.2% probability it's a bird, 0.4 it's a cat, and so on and so forth. So with very high confidence, it says it's a boat. Now, what's going on in the network? That's what we're trying to figure out. If this is a neural network, so what we have is in layer one, we see that it has, so this is a convolution layer. Don't worry about pooling and fully connect. I haven't decided, explain them. But if it's the first convolution layer, if you see what it's trying to figure out, so it has found all the color-based information. So all the color and gradient information. In the middle layer, it is automatically learning all the like transitions or all the edges and all the different spherical shapes, patterns, contours, and so on and so on. As we go deeper in the network, we see that the network has learned more of the higher level things. So this is the texture from a petal, this is the texture from some bird's hair or something, and these are spiral textures. So these are all textures which were present in the image, right? So essentially, if you give it, say, human faces, it will learn, say, the eyes, the nose, the mouth, so the important features of the human face, right? For dogs and cats, it will, so these layers will learn things like the paw, the claws, the dog's eyes, and so on and so forth. And based on learning these information is how it can decide whether something is a dog, cat, bird, or a boat, and so on. And this learning is done automatically if you give it that like feed forward and then backward training, cyclic training process. Right? I hope you get the intuition behind this. So now I wanted to go through a small Cookbook example. If you want to just jump into machine learning, because it's a very hot topic right now, and then do some computer vision. So the reason I chose this is because there is already a very good tutorial of it in the TensorFlow website. So if you go to TensorFlow.org's tutorial and Keras, so TensorFlow has tons of these kind of tutorials, and it's very well explained. So you can go and check it out. By the way, TensorFlow is by Google, if you guys don't know that. So they document stuff pretty well. So the example that we're trying to do over here is you have what we call handwritten data set, which means this data set consists of these handwritten digits. So they have collected like the handwritten scripts of thousands of people, and they put it in a data set. And so what the neural network is supposed to do is, if you input it any image, it is supposed to tell you whether this digit is a 0, 1, 2, up to 9. So it will tell you what the digit is, right? And these are some of the good examples. There are some very tricky examples where even if you look at it, you cannot tell whether it's a 7 or it's a 1. So for instance, let's say this image right here, it's actually a 7, but it can be so similar to a 1, right? Or this can be a 7 as well. So you will see that the neural network does, or this, for instance, this guy is supposed to be a 5. It looks like a 3 to me. So you will see that the neural network does a pretty decent job at analyzing these kind of tough handwritten digits as well. So so if you're familiar with Python, this script is in Python. But if you're not, don't worry. I think it's easier if you use Python for machine learning first as a starting point, but you can do it in so many other languages as well. MATLAB, for instance, or R, Octave, C++, so many things. But this example is in Python. But so you have to import a library, which is the TensorFlow library at first. And then, so TensorFlow library already has the data set. So if you want to work with some other data set, you may have to manually download it from the website and then work on that. But TensorFlow, so MNIST dataset, which is the handwritten dataset, is already there. So this thing loads it and splits it into a training and test. So this test, we are keeping it for later to analyze and see how well our training performed, right? So this is unknown data, and we will be training our network on this data. This part is just the normalization. I'm not going through it in much detail, but I kept this part to say that normalization is very important in machine learning or in computer vision. So what do I mean by that? I mean that you have to make sure that if you take your images, they have the same kind of, they have the same size, or all of them are RGB or color images, then you should be consistent and feed color images. You cannot go one color image, one black and white, and so on and so forth. You have to make sure that things like, so we are dividing everything by a 255, so it's in the 0 to 1 scale. That way it performs better. Everything is a float because we don't want floating point of like division errors and stuff like that. So these kind of things you have to take care of before you can feed a data to any system. Otherwise, you will just get bad output and you won't be sure why. The network is not learning anything from your pixel values because the pixel values are not on the same scale. This TensorFlow model building an architecture which looks like this. So it has a convolution layer, which we just discussed. Then it has a pooling layer and a fully connected layer, right? So what you can do in the actual system is you can go ahead and add this thing. So we are just adding a convolution layer, a pooling layer, and there we are adding the dense layer. So I wouldn't explain what dropout is, but you can look it up. So this flatten is a technical thing to put it into a dense layer. Convolution layer, you already know what it is. So pooling layer essentially is if your input image is like this. So what it does, it splits it up into boxes and just takes, so whatever is the highest pixel in these four. So 6 is the highest pixel, it takes 6. In these four, 8 is the highest, it takes 8. In these four, 4 is, it takes 4. Over here, it takes 3. So pooling, what it does, it extracts the more important pixels or the more highlighted pixels, and it gives you a smaller version of the an image, so almost a pixelated version. It helps us get a holistic sort of view or an overall view of the images. So that's why people do pooling. It's a very, and then at the end we add a fully connected layer. So fully connected layer is so this is a dense fully connected layer. Every node is attached to everyone else. So that's a very standard thing which people have been doing. And you put this layer to like provide the model with more opportunity to mix the signals, right? So you don't want the learning process to be totally like this part of the network learned something and this part of the network learned something completely different. You don't want that. You want your signals to mix so that it can give you a holistic or a overall view of what this digit is. So people put in a dense neural network at that. So again, as you can see, this network is outputted 9 with a probability of 0.8. This shows you how you can fit. So model.fit means I'm fitting in the training and test data. So remember, I got the training and test data from my first part. This thing is just setting up the neural network. This has got nothing to do with the data you are working on. And then over here, finally, you fit the data. 10 epoch means, so remember the forward and backward pass, we will go through that pass 10 times. So we also have something called loss and optimizer, which I don't want to get into too much details because there's so many things you can talk about. But loss essentially is a penalty for a bad prediction. That means when the network is going forward and it sees how bad its prediction was, calculates the loss, and then in the backward pass, it assesses and updates the values based on how bad its prediction was. So that's what loss does. And optimizer is algorithms used to like change the attributes of neural network, such as weight and learning rate, in order to reduce the losses. So optimizer help us reduce this loss quicker, if you mean. Right, again, you can look these things up, and if you don't understand the basics, don't worry too much. So finally, we evaluate on the test data set. So these are data sets the model has never seen. And then this, if you type this line, it will actually give you the accuracy of your model and say, okay, I was successfully able to tell you these many were correct and these many were wrong. So of course, so X test is the image. So these are the image input and this is the label of the image. So 1, 2 or what. And then I've just plotted a sample output saying that, okay, this is 9. And then if you print the prediction of this, you will just see that this is a 9. The machine has predicted. Right. So that's more or less an example of neural network, how it's done. All right, so this was like a small cookbook example of how neural networks work in general. So yeah, look it up if you want to play around with it. There are so many cool things to do with it, and you can just use it in your own laptop. You don't need fancy CPUs and stuff like that. So this is very easy to do.